Now let's think about collisions in a bigger way. Let's think about collisions as describing how multiple bodies move as a system. How you can take a bunch of interacting objects and think of them as one big object with internal interactions going on. We've actually sort of been doing this. We've been thinking about impulsive masses, is my nickname for them. That basically means we have M1 and we have M2, and they're headed for each other, and they have some sort of either elastic or inelastic interaction, and we've calculated everything that happens, the initial and final velocities. We could think of that as one object just going through some internal interactions. Another would be interacting masses. So here, these are certainly interacting, but it's very impulsive. They ignore each other, and then they hit each other, and then they interact. You could also have bodies that interact all the time. So the good example is the solar system, right? So all the planets in the solar system are interacting due to the gravitational interaction with the sun and each other, and there's moons around the different planets and all this stuff. It's all going around, all these interactions. But you can think of the whole solar system as just moving in its orbit around the galaxy, right? So there's also this. This is also a system of particles, system of masses. And then finally, the third category, I would say, is solid objects. And the classic physics solid object, is the wrench. Here, let me just, here we go, a wrench. This is always the textbook solid object. Here we go. I'm going to give you a perfect drawing of a wrench. Wow, look at that. Yeah, that's not much better. A wrench, a solid object, is really a collection of little individual atoms held together by chemical bonds. But you can actually think of that as a bunch of little elements all interacting and acting as one object. Right, this is the easiest one to think about because you think of a solid object as a single particle or a single mass. So if we want to think this way in terms of collisions, sort of two important points. Let's see, one is if there are no external forces, if there are no external forces, the total momentum of the system is conserved. So we still have conservation of momentum. Nothing special here is conserved. All these interactions are internal, therefore conservation of momentum still exists for any of these as they evolve. So we'll use this a little bit. But the more interesting, insightful one is this. The system follows Newton's laws like a single object at a location called at its center of mass. All right, this is the concept we want to talk about, the center of mass of a system. So we can think of each of these as having a center of mass, and in terms of that center of mass, the object is just moving along, obeying Newton's laws. If there's no external forces, it's either just sitting still or it's moving at a constant velocity because it has a constant mass and it has to have a constant momentum. The whole solar system is just drifting along, even though all the orbits are happening inside. If I throw this wrench, it'll just move along. So we're going to work on a few of these mathematically and see how we can use these ideas to solve problems. Let's look at this concept of the center of mass. Let's start by calculating the center of mass for several masses in 1D. So this is kind of like the problems, the collision problems we solved. But now we could increase our complexity a little bit, have M1 here, and then have a small M2 here, and then have a big M3 here. Let's imagine those three are going to collide. They have some velocities one way or another, and they're going to run into each other. But instead of thinking about momentum and energy, we want to think about this problem in terms of center of mass. So all we really care about right now is let's calculate the center of mass. So to do it, you've got to define a coordinate system. All right, so we're going to start with the origin here and make this the x-axis. And then we can define the position of each of these on that coordinate system. Okay, so they sit at positions x1, x2, x3. x1, x2, x3. All right. So the simple formula for finding the center of mass is this. It is x, center mass of this system of particles is, on the bottom you put the total mass, m1 plus m2 plus m3. And on the top you put the position of each one times its mass. All right, so this is m1 x1 plus m2 x2 plus m3 x3. And if there were 4, you would just add another term here and another term down here. Really what this is the mass-weighted position. If you put a lot of mass out here, it pushes the center of mass this way. If you put a lot of mass here, it pulls it this way. So if you're familiar with weighting, this is basically just mass-weighted position of an object. If you had n particles, if we wanted to write this real general, we could say that the center of mass, we could put a 1 over big M, where big M is the total mass, and then just sum up all of the x, well, I guess we'd call it I. I'm sorry, I usually put the mass first, mixi, for I equals 1 to n. If you want a general formula, there you go. But it's a simple idea, 1 over the total mass, and then the mass-weighted position of each one. So let me just give you, instead of doing a problem, let me just give you an idea that this is true. Let's go back to our equal mass elastic collision. And let's watch what happens in time. Let's make a movie here of the equal mass elastic collision. We had mass here and a mass here, and it approached. And then we had a mass here and a mass here. And then they hit, and remember, they exchanged velocities. So this one stops, and then this one keeps going here. And then after a little bit far longer, this one is out here, and this one is about out here. So this is in time what would happen. Right? Remember, like that, and like that. So if we follow this formula, we could say, where is the center of mass of two equal masses? Well, let's see. We could say if we just had two of them, and if they were equal, you'd have m1 times x1 plus m2, or you'd have m1 x1 plus, I'm sorry, you'd have mx1 plus mx2. You'd have 2m in the bottom. So the m's would cancel. You'd have x1 plus x2 over 2. x1 plus x2 over 2 would basically be in the middle. So the center of mass of two equal masses is always right between them, just between them. So here we would say the center of mass is here. Here we'd say the center of mass is here. Here we'd say the center of mass is here. And here we'd say the center of mass is here. So even though these two things had a collision, and this one was going and it stopped, and then this one was stopped and it's going, and they hit, and there were repulsive forces, all this exciting stuff, if we watch this in time, what did the center of mass do? It just moved along. If you think of this as a single mass, it followed Newton's laws. There were no external forces. It just drifted, okay, despite my artistry here. So this is how this idea works, is if you can calculate the center of mass of something, suddenly it becomes just an isolated particle, and you just have to watch it move. So now I want to just give you a few formulas where if we wanted to expand this to 3 dimensions. So in 3D, you wouldn't write it in terms of x. It's simply the same formula, just with the position vector. Right? If we had these distributed in 3D, you'd still have to find an origin. You'd start drawing position vectors to all the masses, and it would basically be the same. It would be 1 over m, and you'd just say m1, the position vector 1, plus m2, the position vector 2, plus dot, dot, dot. And you add up all the masses. Or you could write it as a sum, either way. But then it gets kind of interesting. What if we take a time derivative? What is the time derivative of the center of mass? This is why it's useful here. A time derivative of the center of mass is d dt of position of the center of mass. Well, that's the velocity of the center of mass, right? So that's 1 over the big mass, doesn't depend on time. And then the time derivatives here, well, that's constant, but dr1 dt is the velocity of mass 1. So mass 1 v1, right, plus mass 2 v2 plus ... all the other masses. But if we bring this over here, then what we get is the total momentum, right? This is the big M, all their masses times all their velocities is equal to that. And then these are the individual momenta, right? The mass times its velocity plus P2 plus ... So it's really just like conservation of momentum. If you take the momentum of each individual particle and you add them up, you get the momentum of the entire thing. But the entire thing is moving at VCM. So you can think of it as an object moving at the velocity of the center of mass. So that kind of confirms that. That makes sense, right? And then what if you take another time derivative? Time derivative, and you ask how fast is this object accelerating? Right? Another time derivative, the total mass is constant, but this becomes big M times the acceleration of the center of mass. Well, that's equal to the sum of all the p's, dp, dt. The sum of the dp, dt. So that looks like Newton's second law, right? So that's what you would expect. We're saying you can treat this thing as just a simple particle. Well, it's going to, at the center of mass, it's going to obey Newton's second law. So you can actually use all this to redo all those problems, right? So all the problems we did about collisions, you can also calculate them, assuming the center of mass evolves like a particle following Newton's laws. But you really get the same answer as doing momentum and energy. So usually you just do it with momentum and energy. But I just wanted you to think about it this way, because now we're going to extend this to larger objects.